Hello everyone, welcome back. I'm your friend in XO. Today, we're going to try to know the text generation by using F network. To be honest, I don't know what the F network is, but we're going to know this, right? For now, the GitHub Pioneer is quite hot. By using that tool, you could have the code auto completion. It works just like magic. What I mean is exactly this little tool. It's quite useful to be honest. So based on that technology, I think okay. In other words, because that technology is quite useful, that's why we know it. Okay, introduction. The original transformer implementation was one of the major breakthroughs in natural language processing, giving rise to important architectures such as BERT or GPT. However, the drawback of these architectures is that the self-attention mechanizing they use is computationally expensive. The Fnet architecture proposes to replace that self-attention with a much more simpler mechanizing, a Fourier transformation-based linear maximum for input tokens. The Fnet model was able to achieve 19% of BERT's accuracy while training 80% faster on GPUs and almost 70% faster on TPUs. This type of design provides an efficient and small model size, leading to faster inference times. In other words, if we can reach a high accuracy and while would be able to reduce the training time and speed up the inference time, then that's a good thing. So let's say how can we use this? First, we import the TensorFlow STF and import the carriers. I guess you guys already know how to use them. It's quite simple, so I just run that. And then we have defined some hyperparameters that matter for now. Those things are just numbers. Then we can load our data. We will be using the Cornell dialog couples. We will parse the movie conversations into questions and answers sets. So when you look at this, you would generally notice that there has no question and answer kind of stuff. It's just mean that we want to know what the next sentence in a conversation would be. So in other words, it's just an auto-completion kind of stuff, and it can be, to be honest, any context or any text. For example, a script or a novel or a simply book. Whatever text you want to give it, that would be fine. But for now, we will use a movie conversations. So what he did is he used the keras utils to get the files that it needs, and then he read that files right in here. It's a text file. Then he somehow wrote a function to do the pre-processing for the raw text. Those are just normal Python code, so we won't explain that. You can check it by yourself. Okay, after the running should set it up, but before he goes any further, I'd love to add a code block here, since I want to know what kind of data eventually we got. So let me say I just want to know the crossing, the first element of that crossing. Here we go. It's just a string. It's just a sentence, nothing else. If we print out the answers, the first element of the answer list, we will also get a sentence. Then we get our train dataset by using the tf data.dataset from tensor slashes. No, it's not tensor slashes. It's just a list of, let's say, strings. So yeah, even that, I still do not know what's inside of the train dataset. So I just print it out. Okay, so it's a type that was defined by the TensorFlow. It's called the tensor slash dataset. What kind of function we can use for it? Here we go. We got a lot of functions that we could use, but to be honest, I don't see anything that's familiar. So I just leave it there. All right, let's get into the next part. pre-processing and tokenization. Pre-process the text. If we give it a sentence, we're gonna convert all those characters to lowercase. Then we're gonna do a regex replacement. For example, we're gonna try to replace every question mark and this mark into this symbol. I don't know why this symbol, but let it be it. Then in the second line of code, we're gonna replace every new space into a single or new line. We're gonna replace every new line into, oh sorry, this is not new line, but we're gonna convert all those continuous spaces, which means a lot of spaces, into one single space character. Then we're gonna replace a non-English word with spaces because we would only love to process the English for now. We don't want to mess up the data, so we're gonna convert all those non-English words into spaces. Then we're gonna do a strap so that we could remove the head and the tail duplicated spaces. Then we're going to add the word start and the word end into that sentence, so the program would know where is the start and where is the end of that sentence. Okay, after that we do, let's say, layers, the text vectorization. To be honest, for now, the machine learning has already been in a level that you don't have to manually do anything. The framework does everything for you. So all you have to do is to memorize those function names and how to use those functions. That's all. So what the vectorization function does is to convert the pure string text into matrix or vectors. Of course, we're gonna specify the VCAP size. What is that? Oh, the VCAP size is 800. Oh, sorry, 8100 or 8000. What does this mean? Is that this is the whole number of individual words, or how many different words we have in the whole conversations. We're gonna set it to 8,000. But if you are doing some stuff with the Chinese language, that could be much worse because it could be at least 10,000. Then the standardize equal to the pre-processing text, which means this is just a function. What it does is to convert the raw text into the text that we wanna do the training with. Then the output mode would be integer, then float number. The output sequence length equal to the max length. This is the hyperparameter that we just defining somewhere. Here we go, max length. So for a sentence, the max length for it would be 40. Then we will adopt the vectorizer to both the question and answers. This dataset is bunched to parallelize and speed up the process. Okay, so what do? We say tf.data.dataset from tensor slices. Then we both have the question and answer with a batch by something like that. Why we use this line of code as a batch? Because we want to have multiple students that doing the work at the same time. And why we define the vectorizer, because we're gonna use it right here. Okay, after that, what do we do next? Tokenizing and padding sentences using text vectorization. So here we just defined another function. And for this function, what it does is to take the input and output. Why he also take the output out there? I don't know. But as you say, what this function does is to use the vectorizer to convert the inputs into the outputs that we want. Also, we're doing the same thing for the outputs, and we're gonna do the padding. You know, if you ever do if you have ever made an user interface, you would know the meaning of the padding. Well, it's just let's say if at the first you get if you got A B C D 4 character, and for the second row you only got A B. So for now it's not so good. We're gonna do the padding, which means we're gonna add 2 empty spaces for it so that they would look like have the same width or same height. Normally that would be just something like this. I hope you understand that. If you don't, just do a search. here, if you go to the definition of this function, you would know that a padding D0 indicates how many values to add before the contents of the tensor. And if you get the D1, indicates how many values to add after the contents of tensor. So in here, after the contents of tensor, he said that he gonna add some extra value to the right, which is after the contents. He gonna add a 0 after the contents for the outputs. Yeah, I don't know why here he only did the padding for the output, but he didn't do the same thing for the inputs. But let it be. We don't want to worry about it too much since that is not worse. It's just a small part of the whole picture. And what it returns is the encoder inputs, which is the input, then the decoder inputs, which is output, and the outputs. I don't know why. Oh, here we go. Encoder input equal to that input, decoder input also equal to the output equal to output. Yeah, that makes sense. But anyway, let's go on. We're gonna define the train datasets by doing a map. How? Train dataset.map vectorize text and the evaluate datasets equal to also that. And for each one, we're going to add the data into it. This is how we do it. We did a supper, which is do some reading nice. Then we did the bench. Actually that's pretty fine for now. All right, now let's have a look at the Fnet encoder. The Fnet paper proposes a replacement for the standard attention maximizing used by the transformer architecture. Yeah, something like that. We got our input. And for this input, we're gonna have the word position type. We use a foreigner to do some processing. Then we normalize the stuff and we do the feed forward. After that, we normalize it again. In the end, we pass all those values into the dense network. In the end, we output the projection. We get our output. The outputs of the FFT layer are complex numbers. To avoid dealing with complex layer, only the real part, the magnitude, is extracted. So the foreigner function will output the complex number. That is something that I don't know. But he will only keep the real part. The dense layers that follow the foreigner transformation act as convolutions applied on the frequency domain. Then we're gonna implement the F network, which is this graph. We're gonna implement its encode. And let me try to understand this, even though I'm not so good at the mathematics, but we can try it. So the initialize function, it will have the embedded dimension and the dense dimension and a bunch of arguments. Then we're gonna pass that arguments to the Fnet encoder itself. Yeah, I don't care. Then we're gonna define the embedded demand, dense demand, equal to 2 of that, and we also have the dense projection. It's equal to the carrier sequential with 2 dense layers. This is something that we know long time ago. Then we're gonna have 2 normalized layer, which can be implemented as simple as layers that layer normalization. Then we're gonna the call function. This function would be called for every step of the training. It will get the inputs and we're gonna do some calculation in the end. We output the outputs. Yeah, we somehow casting the inputs to complex. Then we use the FFT2D, which is a foreigner transformation. Even if we do not know anything about the mathematics, we could still use this function. That's the power of programming. And somehow we get the real part of that complex number by using this function. Then we do the normalization. After that, we pass the output of that into a dense layer. And in the end, we do the normalization again. We return that value. So it seems like if we can understand this map, we can actually create the model by ourselves without any problem. So for now, I think the machine learning is quite easy, but a few years ago, I feel like I don't know anything. Then let's go on. We're gonna create the decoder. The decoder architecture remains the same as when proposed by someone in the original transformer architecture, consisting of an embedding, positional encoding, to mask the multi-head attention layer, and finally the dense output layers. The architecture that follows is taken from a book, I guess. So we're gonna try to create the decoder. Am I right? So from here we could know that we created a decoder class. But what about this? Positional embedding. What is that? I have no idea about that, but it seems like it will take the sequence length, the vocabulary size, and the embedded dimension kind of stuff. I think this is probably the format of it, of the matrix, or the, let's say, the shape of that matrix. So we're gonna say the talking embeddings would be equal to layers embedding by giving the input dimension, which is the vocabulary size, and the output dimension, which is embedded dimension. And we're gonna do the same thing for the position embeddings. We will have the sequence length, vocabulary size, embedded size, and we're gonna have a call function. For this call function, you will get the shape of that inputs. Anyway, it did all those things out there, and even he did the mask. You know, if you have ever used the OpenSea way, you would know that what's the concept of a mask. It's just about, let's say, if you have a shape, black and white shape, or any color stuff, you want to extract one part of that shape. How do you do that? You do it by giving it a mask. A mask is, it's just a matrix or an image where only have white or black values, which is 0 and 1. And then we're going to use that mask, or use that image, or use that matrix to get some part of the real image. I don't know if you ever heard about that. If you don't know, just do a search OpenSea mask, and you should probably learn something from it. Now, let's go on. We're gonna go to the Fnet decoder. For the decoder, what it does is to get the real information from the tensors or vectors or matrix, any way you call it. And here, if you want to implement the attention layer, all you have to do is to call layers that multi-head attention, which is so convenient. I don't know. You know, back to before, this requires a lot of work, but for now, we only have to call one single function and it will be done. Then everything else is probably the same. After the initialize function, we would like to define a lot of layers or some parameters that we want to use, or we're gonna yeah, that's exactly what we're gonna do inside of the initialize function. And then in the call function, what we do is to take the inputs, which is the data, and take the outputs. We're gonna use that data to let that data pass through all those layers that we have defined previously. So what we're gonna do is to use self-delegated casual attention mask. We're gonna take that input and output the mask. After that, if the mask is not known, we're gonna do some processing for that mask. Alright, then we're gonna get the attention output by using the attention layer that we just defined in here. Okay. Then we're gonna do a series of processing in the end. What we do is to put all those stuff into the dense project. Then we do a formalization for the output. Okay, something like that. But to be honest, those processing, those code inside of the call function can be changed to whatever you want, since at the beginning you don't know which architecture is best for solving your problem. So you probably could do whatever you want, and in the end, you would find the one that maximize the prediction accuracy, I guess. And if it does, then that's the best architecture. Okay, so let's get into the next one. Oh, this is a function that we have. Get a casual attention mask. Yeah, I don't want to look through it. It seems so scary since we have no idea what he was doing. But you know, we know what he was doing. He was making the mask by filtering some values out. But for the details, I don't care. Then the final important task for us to do is to actually create the model. You know, Since machine learning has a lot of developments in recent years, so at the very beginning, we would probably just get started by strictly develop our model. But for now, since it's getting generally getting more and more complex, so we at the beginning we have to define a lot of classes, a lot of sub models or sub layers, or in this case, what do they call it? They call it functional Keras API. I don't know. So in this case, you have to first define a lot of sub model or sub processing for your model. Then you're going to combine those things together to create your own model, which is just a series of calculations. So we're going to do that. Encoder inputs equal to Keras inputs. We're going to do some processing for the inputs. Maybe not the process, but we have to define the inputs first. Then we're going to use position embedding to get some value from that input. Here it's x. But the x is not the final output. We're going to pass it as an input to the Fnet encoder. Then we get the encoder outputs. And for the Keras model, it will receive an input and output. And we're going to say that it's an encoder. And for the decoder inputs, that'll be another one. It will take in from, we're going to give it a len, right? We'll give it a len called decoder inputs. And then the encoder sequence inputs equal to something like this. We will also need to give it a len, decoder state inputs. Then we do some processing with decoder inputs, with the encoder sequence inputs, and we do a dropout to drop out 50% of those narrows value. Then we have to define the dense layer, because in the end, as I think from my experience, they would normally at the end goes into the dense layer. I don't know why. Then we're gonna actually define the decoder, which will take the decoder input and encode the sequence inputs and output the decoder outputs, and we're gonna give it lambda outputs. Okay. Then we can define the decoder outputs equal to the decoder with the decoder inputs, encoder outputs. And we define our model. This model will take the encoder inputs, take the decoder inputs, and output the decoder outputs. And we're gonna give it a len called Fnets. In the end, we return that model. So as you could say, this is getting very complicated. You have to pass it all around from here to there. But in the end, what you really care about is this one. This is the input, and this is output. All right, then after we have defined this function will return us a model, which is Fnet model. Yeah, I don't care. Now, for now, what I'm gonna do is to run those code block. I forgot about to run all of them. So let me do that. The first one, the second one, third one. We get an error. Len adopt is not defined. Okay, here we go. We run it again. All right, now we get into this process. We're gonna get that model and do a compile for that model. Then after that, we will have to pass our data into that model by using the fed function, which can be quite simple. Let me just run it. So this is actually the training begin, where the training begin. And this function will take quite a while. So I'll just pause this video and wait for it to be finished. Alright, it seems like we just finished the training. How about we do the testing for now? Before we get started, to be honest, I was quite curious about how he was able to do the reference. It seems like he just write another function called decoder sentence. So what he does is he takes that sentence input, then he did the vectorization with this. Yeah, after that he expanded the dimensions. Then he did a nope. For I in range of max length, predict equal to TF that expand the dimensions tokenized input sentence, which is a sentence, right? Then the decoder inputs, what is that? It also has the tokenized target. Sorry, not tokenized target sentence. Oh, okay. So the target is a vector that only have the start word. So at the beginning, we gave it the input sentence, and we also gave the target sentence, the decoder inputs, the start of that. And then for the prediction, we choose the most probable value out from it by using the argmax function. And if the last prediction is equal to the end, then we break it. Otherwise, we would add that word to our decoded sentence. At the beginning, it's an empty string. And also for each time, we're gonna add the tokenized target sentence, which is a vector. We do a concatenate with the one that we just got, so that it will keep predicting the next word, I guess. Since this is a for loop, and the max prediction it would get as 40, since we have set the max length to 40. Okay, that's how it works, and we could try it out. Let me just run this. Here we go. Where have you been all this time? I'm not. What is that? Let me try it again. So this answer would get changed for each time when we do the training. But it will, let's say it will get into a stable answer. If the training goes, let's say if we do a long time of training, eventually we'll get a certain answer. Okay, so this is the learning part for the text generation using F network. In the next video, I'm going to do it by myself. I'm going to train my own F network using my own datasets. So that will be the practical part of this one. So I'll see you guys in the next video. Bye.